And start now.
All right. Thanks for the invitation and thanks for organizing this workshop. So it's going to be about Clifford algebra representations for deep learning. So I already had a nice introduction, but very quickly, I'm a PhD student at the Machine Learning Lab in Amsterdam, working in AI for science, generative models, time series, and geometric deep learning, where I used Clifford algebras to construct neural nets. So today I'm gonna give a quick introduction to the Clifford or geometric algebra, then how we constructed neural networks using this thing, and then some extensions to simplicial message passing and convolutional neural networks. So this first paper that I will discuss is this paper, Clifford Group Equivariant Neural Networks, done with Johannes and Patrick, one of my supervisors. But before we get into it, like quick background on equivariance. So equivariance is about equipping models with a sense of symmetry in the data. So very simple example, if we try to make a segmentation map of this cat, then of course, so we are trying to classify some semantic features in this image. And of course, if we reflect the image, then the segmentation map should also correspondingly reflect. Similarly, in the sciences, when we given a structure of a molecule, then we can use a a neural net to predict the forces on the atoms, and then of course, if we rotate the molecule, then the forces should also rotate. And finally, if we are predicting dangerous objects at the airport, then permuting the object should also make your prediction commute. So this stimulates robust and reliable results in deep learning, which can be elusive. But maybe what I like more about it is that in some sense, we are not preferring one frame of reference over the other. And this is, of course, very fundamental in physics, where a lot of theories are built upon symmetries and being able to agree on certain quantities, irrespective of the frame of reference you assume. And this is kind of it's very elegant, and we want to maybe equip our neural networks also with this idea of frame independence. And using group theory, this is formalized as applying your model and then applying an action from your symmetry group should give the same result as going the other way around, which is shown in these commutative diagrams. So there's a lot of literature in this direction. For example, we have methods based on group convolutions. So they integrate over entire groups. And maybe most famously, convolutional neural networks integrate over the translation group. But if you want to do this for other groups, then this quickly becomes computationally intensive. Other methods, they try to extract invariants or scalar features from the data. But we find with the current methods that this can sometimes restrict their expressivity somewhat. And finally, there's a popular direction built on E3NN using Clebsch-Gordon coefficients, spherical harmonics, and so on. So this can maybe get a bit complex, and also it's not trivially extended to groups other than O3, which is the core focus of this direction. So in one slide, we to get kind of an idea of what we're doing, we operate on these objects called multivectors, which are elements of the Clifford algebra. So here you see an example of such a multivector in the three-dimensional case. It can be decomposed into linear subspaces, such as a scalar part, vector part, bivector part, and a trivector part here. And we can act on it using our neural net. Here we just scale one axis for visualization purposes. And we have an orthogonal representation on this Clifford algebra, such that this, again, the diagram commutes. So about the Clifford algebra, it's also known as the geometric algebra. This can sometimes be a bit confusing, but it just has two common names currently. Now in physics, it's can be used as an efficient algebraic representation and way to manipulate certain geometric concepts. It generalizes the exterior algebra if you're familiar with it, and you can get behavior similar to complex multiplication, quaternion multiplication, and so on inside this algebra. But what's especially cool is that a lot of theory can be derived or results can be derived in this algebra that are coordinate or dimension independent. And that's also what we'll use in this presentation and in what we did in our work. And I'll come back to that later. And finally, it's been used in various applications. So why do we need it in deep learning? Well, there were some early indications that Clifford algebra representations and weights can yield more efficient learning and generalization properties, similarly to how complex or quaternion neural nets have been used. But maybe what I like more about is that we can represent using these linear subspaces that I showed certain physics quantities faithfully. So like a magnetic field can be faithfully represented using a bivector subspace. And using the fact that I said that a lot of these results generalize to several dimensions. That means that we can get equivariant neural networks with respect to several groups, so orthogonal groups, Euclidean group, and so on. And this is all powered through an equivariant multiplicative operation called the geometric product. This means we don't need spherical harmonics, the Gordon coefficients, and so on. And also the nice thing about it is that this Clifford algebra space is closed under multiplication and addition and so on and so forth, as opposed to, for example, tensor algebras, which can grow indefinitely. Or make this more clear, we have to start with bilinear forms. So geometry starts with the notion of distance, which can be obtained using bilinear forms or inner products. Basically a map taking two vectors and yielding a scalar. So if you define this through a bilinear form, you now have a way, or in the typical Euclidean cases, you have distances like this. You can compute angles. So geometry starts with taking a vector space and finding a certain way to compute these geometric quantities. And this, as a side note, directly introduces the orthogonal group, where we have this inner product or bilinear form, and we define the orthogonal group as those linear transformations that preserve this inner product under transforming two vectors with those matrices. And of course, in the typical case, this corresponds to things like rotations and reflections, which preserve all the angles and distances. Now, this definition generalizes directly to non-Euclidean metrics, for example, in special relativity. So in the Euclidean case, we have an inner product, for example, like this, where you have a metric that can be, that's the identity matrix. But people like Einstein and Minkowski, when they were studying the unification of space and time in one geometry, realized that to make that work, you have to go to Minkowski space, where you apply a non-Euclidean metric shown here. But the orthogonal group is then still defined completely analogously, namely those matrices that preserve this inner product. And to indicate the signature or of the space, like what this matrix looks like, we write 013. Okay, so back to the Clifford algebra. So we have a vector space, for example, R3. And we want to equip it with a product now. So we can write U times V, which is not something you typically do in linear algebra. But what this product means is, we wanted this product to relate to the geometry. So as I said before, that was defined through this bilinear form or inner product. But we don't necessarily want it to always reduce to a scalar, which is what the inner product, of course, does. To be able to compute maybe more meaningful features in our network later on. So to do that, we make this axiom saying that whenever we square a vector, this should give its squared norm, or this inner product with itself. And this is how we relate the product to the geometry. And then we can do algebra. So we can now take the square of two different vectors and expand. And then we see that multiplying uv plus v, or evaluating this expression, gives 2 times the inner product. And basically, that's by this definition in math. But in what space, like what's really happening when we take products like this? That's what we'll look into now. So we look at where does this lead us? So again, we start with R3, and we take a basis, an orthonormal basis, meaning we can write any vector as a linear combination, of course. And then the Clifford algebra over this R3 with a certain inner product creates this basis, where we, as you saw before, we have these different linear subspaces. Again, we see that we have we start with vectors, as we did, but now we can create objects by multiplying, called bivectors and trivectors, which you can interpret as oriented areas and volumes. So the vector space is growing by allowing for these kinds of products. And we get scalars because of the fact that when you square vectors, you reduce it to an inner product. Now, to convince you colloquially that this is all we get in the 3-dimensional case, I'm going to give you the following argument. So for orthogonal vectors, we always have this identity, anti-commutative identity. And this follows from the fact that we derived this identity on the previous page. And then for orthogonal vectors, this is, of course, 0, giving you this anti-commutativity relationship. When I now take the highest grade, what it's called element, this trivector, so E1, 2, 3, and multiply it again with one of the basis vectors, then we can apply this anti-commutativity relationship twice, swapping E1 and 3, picking up a minus sign, and doing again with E1 and E2. And we see that we get E1 squared here, which reduces to a scalar, of course. And this is again in the bivector subspace. So the space is closed under multiplication. So that means that every multivector can be written as a linear combination of these basis elements. Yeah. And now you might ask, my data usually contains scalars or vectors and not multivectors, but you can always embed your data in this extended space by just considering the multivector subspaces, of course. So you can put your vector data in the vector subspace, and it will be transformed correctly and treated correctly as a vector. So when we let's look at if you now give me some coefficients and I have my basis, how to really compute a geometric product now in terms of coefficients. So here we have a Clifford algebra over a 2-dimensional space, and I assume typical Euclidean case. You give me your coefficients, I expand them in my basis, and I write down the product, and I just expand. So I expand the one term and then again. And we see that so coefficients can always go up in front, of course. Then we get E1 squared here, and we get E2 squared here. They, of course, reduce to scalars. Here we get E1, E2, E1, but with the anti-commutativity relationship, you can swap those, picking up a minus sign, which gives us our bivector part. And when you can identify, or you can recognize that this is an inner product, and this is a wedge product, if you're familiar with it, computing the signed area between the two vectors that we just multiplied. Yeah, so that's an example of how you numerically compute geometric products. Okay, so in this work, there was some echo already before. Okay. Yeah, so in this work, we study how the orthogonal group acts on this entire multi-vector space. And we show that yeah, the action we have satisfies orthogonality. But also we show that the action is additive, so it commutes with addition of these two multi-vectors. It's multiplicative, so it commutes with multiplying two multi-vectors using this geometric product. And it commutes with scaling, so using just real or whatever field you're using, scaling of these multi-vectors. And yeah, so we have an orthogonal multi-vector representation. But these three mean that all polynomials, which of course use these properties, are equivariant. And we can learn coefficients because of this scalar commutativity property. And that's basically what we build our net, or on that idea, we build our neural network. So we define linear layers, then we have some nonlinear gating layers, and we have these geometric product layers. And when we stack these, when you stack multiplications, you get these higher order terms, if you imagine a polynomial. So in some sense, these neural networks are implicitly big or learning big polynomials. So let's look a bit more at the details. So the linear layers, so we always consider a set of these multi-vectors as our inputs, or at any layer of our neural net. We can linearly combine them using learned weights. So we have linear maps that basically for each output channel linearly combine the input channels, meaning we have weight matrices just like your typical neural network, but now combining these geometric objects instead of just scalars. More densely, we can have separate weights or separate linear maps for each of the grades, those linear subspaces. So what that looks like visually is you have your typical feed-forward structure that if you're familiar with it, but now we're not linearly combining just scalars, but we're linearly forwarding these grades. So scalars, vectors, bivectors, trivectors, and so on and so forth. So those are the linear layers. And then, yeah, so that means that we're independently linearly combining these subspaces, but we also want to mix information between them. And that's where the products come in. So geometric product between two arbitrary multivectors can be decomposed into the individual products of the subspaces or the grades. So we can project onto the first grade, which is the vector part of this multivector, and also this part. And we already studied the geometric product between two vectors in the beginning of the presentation. It gave us this inner product and this wedge product. This inner product was a scalar, which is also what we see here. So we have two vectors, and then the output of their geometric product projected onto the scalar part. Here we look at the bivector part, so the wedge product part. So again, a triplet of combinations here. Similarly, we can look at the product between a vector and a bivector and project onto the trivector output part. Now, what I'm getting at is that each of these, if you take two arbitrary multivectors, then their product can be decomposed into all the products between the subspaces, non-zero products are shown here, and each of these triplets, so input out, two inputs, one output, can get one weight, and this is the idea behind these parameterized geometric product layers. So the geometric product between two multivectors, looking at the output grade K parts, can be decomposed into two sums over the two different input grades and a certain output grade, and we can weight that with a certain scalar phi ijk. But as you remember, in our networks, we had these layers consisting of many multivectors. So we can look at any combination of two multivectors and compute this parameterized geometric product. So this is a big layer, but it computes a lot of geometric interaction between our representations. And so that basically again is how we construct our neural nets. Okay, so some experiments. So one of the nice things about this framework is that everything was derived in a dimension-independent way, and also the code is written in a dimension-independent way. So we can, with a change of hyperparameter, we can go from 3 dimensions to 5 dimensions. So that's one thing we show. We basically take this experiment from this paper and I try to approximate this function. And especially given the architecture that we used, we saw that we significantly start to outperform with more data available compared to the baseline methods. Then we look at a 3-dimensional experiment, this n-body experiment, where we have 5 charged particles interacting, and the network is trying to estimate their position after 1,000 integration steps. Now we use graph neural networks because of the permutation invariance properties of this setup. And basically the idea, the idea is that for any node, we aggregate messages from the neighbors, and these messages are computed using a message neural network, if you're familiar with graph neural networks. And we make this message neural network of the type that I showed you just now. So this Clifford group equivariant neural networks, and also the update network. And this means that the entire graph neural network becomes equivariant with respect to the orthogonal group and also the permutation group because of the graph neural network structure. We see that we significantly outperform many previous methods in this direction and are slightly better, but somewhat on par with the SEGNN, which leverages very similar ideas in terms of the setup. And then, so we can leverage the fact that this is independent of the inner product that we equip our vector space with. So we can also go to Minkowski space. So we take data from CERN, where they are interested in jet tagging. So they have data, they smash particles together, of course, causing particle showers. And given the remnants of the collision, they want to identify whether or not at collision time there was a unstable fundamental particle, in this case a top quark. So we have this particle shower data, and we want to predict binary classification. And because things are moving at relativistic speeds there, it might make sense to consider space-time as one geometry, meaning we want to be invariant with respect to the 013 group, including Lorentz boosts. And yeah, it's pretty cool because we can use these same layers and the same code to get results also in this setting, performing on par with the current state of the art, despite some of these methods being specifically designed for these tasks, which was quite remarkable. Yeah, so yeah, basically that's the conclusion of this work, and by using this framework, we were able to solve some of the issues that several earlier methods had, as discussed in the beginning of the talk. So the code is available online. We are currently testing how to, so these geometric product layers, they can be somewhat expensive. So we're playing around with how we can speed this up in various ways. So one of them was using JAX, seemed to help a lot compared to PyTorch. Yeah, so we also have some tutorials there on how to use it. Yeah, and the rest of the talk I'm gonna there were adjacent work. So the geometric algebra transformer invented at Qualcomm using several, and it's Lorentz equivariant follow-up recently. We extended it to simplicial message passing and for convolutional neural networks. And we saw several application papers. Now, in the rest of the talk, I want to discuss these two papers, but maybe it's a good time to do a first round of questions. That's okay. That's it.
Thank you for the talk. Open question. I don't know if that's more efficient, but did you try a fold representation where you use the Hodge dual operator on the n vectors?
Yeah, the Hodge dual is used, but it's not orientation independent, I believe. So you will get SO equivariance, and the experiments we did were we only looked at orthogonal equivariance. So this is on our to-do list. But the Hodge dual is quite easy to implement in this framework. It basically comes, so I don't know if you remember, you had this vector, bivector, trivector part. This trivector, or the highest grade element in the algebra, is always also one-dimensional, and multiplication with an element in this pseudo-scalar subspace is equal to the Hodge, taking the Hodge dual.
Some question? Yes.
Thank you. Just I had a question to understand better the difference maybe with, I mean, there are many differences with normal neural networks, but in this case, the nonlinearity, you don't have an activation function, but the nonlinearity comes from this mixture of inner products, or I mean, all this extra thing you have added, or you also have like nonlinearity at each step.
Yeah, so we also have nonlinearities, but they were basically copies from what was already done. So I didn't discuss them here, and they're fairly simple. But I believe you're right that I need to do some small experiments, but I'm fairly sure that we actually don't need them anymore, because those products, these polynomials, will be nonlinear already. Now, of course, you might want to do some normalizations, because if you have x to the power 9 or something, you might numerically explode. So you might need some normalization there, but I think nonlinearities are not needed anymore. But this is a hypothesis.
Yeah, also a rather open question, probably. I would assume that your model is very expressive if you go up to trivectors. Can you comment a bit about whether bivectors would be very expressive already? Like, do you really need to go all up? Is there some trade-off with resources, efficiency, etc.? Could you comment on that?
Yeah, it's a good question. So as said, for if you want special orthogonal group equivariance, you always need the highest element grade for the reason that it said just now. Then you basically need to force certain subspace elements out. I haven't looked into this yet, but so basically, when you construct this algebra, I just took the entire Clifford algebra as, yeah, you mathematically get it, as shown in the first few slides. I didn't consider throwing out certain grades. I think also if you, yeah, I have to think a bit about it, how to do this.
Thank you very much.
I think we can continue.
Okay. Yeah, so the remaining part will be about extensions on this work, including simplicial message passing and convolutional neural nets. Oh, can you? Yeah. Cool, thanks. Yeah, so the simplicial message passing network. Basically, we say we want to work with data that you can equip with complex topologies, like molecules, proteins, and so on. And graph neural networks are, so usually these are modeled with graph neural networks, of course, which only look at bi-interactions. But can we equip these simplicial can we apply a higher order message passing network while being equivariant to symmetry groups, or the orthogonal group in this case? Yeah, and the motivation to apply higher order message passing is basically graph isomorphism tests. So can we discern one graph from the other with just graph neural networks? Well, there are examples you can find that where that's not the case. So by equipping our data or modeling it with something, neural networks that operate on more complex topological spaces, they could discern two graphs from another. And one way to do this is using simplicial complexes. And yeah, so a simplicial complex is basically you take your set and you define a simplicial complex by taking a subset of the power set, such that all the singletons are still in the set. But for any subset of your power set, all its the subset of the simplex are also in the simplicial complex. So if you take a triangle, where you take three vertices and define a triangle, then all the edges are also in the simplicial complex, and you can go higher and higher like that. So you get simplices of different dimensions. And what people did before in this direction is so in graph neural networks, you have aggregation. You send messages and you aggregate. And this adjacency structure in graph neural networks is very particular. In simplicial complexes, you can define new adjacency structures. So you can have you can look at the boundary of a simplex, the co-boundary, the lower adjacencies, and the upper adjacencies. So you can send messages over these different adjacency structures, and then they update the hidden representation of a certain simplex using an update function, usually also a neural net, that takes the messages sent across these adjacency types. And we basically take this framework and on top of that, do this Clifford group equivariant neural networks. Now, this simplicial message passing and equivariance had been done already, but they usually explicitly equipped triangle simplices with three-way interactions of vectors, like triple products. But the geometric product automatically computes these geometric features for three-way interactions. So we initialize the triangle simplices with three-way geometric products, as kind of shown here. And applying our network, then these features get refined in an equivariant way. Now, to make this more efficient in message passing simplicial networks, they defined 6 new neural networks because of these different adjacency structures. But we reduced this to just one network that shares its parameters. So we basically take this vertex or this set of vertices, and you can lift this to a simplicial complex, but we flatten it in some way again to a hypergraph where we just define new nodes for every simplex, but we still make the network aware of the simplicial structure by aggregating over all the adjacencies in one go, but conditioning the message network on the dimensions of the sender and the receiver. So triangle to edge, you equip the network with those inputs. And that's how the network is still aware of the topological structure. And we applied this to certain experiments. So human walking motion prediction benchmark, atomic motion, molecule, atoms in molecules, their motion, and an NBA player motion prediction task. Again, we can move efficiently between 2D and 3D cases here. And finally, the convolutional neural nets. So this was the most recent work. So in classic, or in when you operate on images, or want to do deep learning on images, then you basically can interpret your image as a function going from some coordinates to this RGB space, of course. This is just 3 scalars, RGB values. But when you go to a more geometric realm, then you have not, or your function is from a Euclidean space to maybe a stack of scalars and vectors and tensors and so on, which can be found in, for example, fluid mechanics. In this case, in this work, what we go a step further and extend it to pseudo-Euclidean spaces. Now, basically what is said imaged here. So you can imagine an image. Again, we now allow for pseudo-Euclidean metrics directly, but typically this is just Euclidean. An image is a function from this base space to 3 colors. You can act on this base space through, you can change your coordinates through rotations and so on. And this induces an action on the output space, and that's shown here. So if we have this bacterium here and we rotate our coordinates, then here we have a scalar field image with just some dots. Then the dots, they don't change. But of course, if you have a vector field, then changing your coordinates, so the bacterium moves, but the vectors themselves, which are on the codomain of your function, should also transform. So you have an action on your base space as well as your representation space. So more abstractly, our functions are now from a base space to some vector space, which decomposes into several types, scalars, vectors, and so on. And we want to learn a map from an input function space to an output function space in a way that it's equivariant. So we can rotate our fluid mechanics field, and the output should also rotate. So for example, in the experiments that I'll show, we give the network an initial condition of some Navier-Stokes system, and it should produce the solution at t plus delta t. Now, this is usually solved with convolutional networks, these kind of tasks, which apply convolutional layers, which are famously translation equivariant, but we want them to also be orthogonal equivariant, for example. Now, a convolutional layer, if you define it in a continuous case, is an integral transform parameterized by this kernel function. So the parameters of your network live here, and this kernel is a function from the base space or a coordinate to a linear transformation. Yeah, so to a matrices, a space of matrices, basically. And people like Maurice Weiler and also Gabriele, who's here today and present after me, they studied this in depth, and they showed that you can design equivariant neural nets by introducing a steerability constraint. So maybe I should not spend too much time on this because you will also talk on this, but maybe, so Gabriele will give more details here. So your kernel should be of a certain form. And what the first author of this work, Maxime, showed in 2023, also with Gabriele, is that this kernel constraint, so the constraint on the kernels to get this equivariant, can be solved by parameterizing this kernel function with a neural net if the neural net is equivariant. So you have a neural net going from your base space into the linear maps. That should be an equivariant neural network. Then your entire convolutional neural network becomes equivariant. So using this image, we have a 3x3 grid, so a 3x3 kernel. Your network takes a coordinate and should give you and will give you these linear maps. Now, the core idea here is to get pseudo-Euclidean equivariance, is to use these Clifford MLPs that I defined earlier. And the whole idea is that this Clifford MLP takes a coordinate, outputs a set of multivectors, which was exactly what it was designed to do. And then this geometric product is a bilinear operation, right? This geometric product, we can multiply two multivectors, but we can fill one of the arguments with whatever the kernel network outputs. And then this bilinear map becomes a linear map. So we can basically, take the output, fill the arguments of a geometric product with what the network outputs, turning the bilinear map into a linear map, which can be used in your CNN using just PyTorch and so on, conv layers. I'm almost out of time, so I will go quickly through the experiments. So we look at, as said, we give the network initial conditions, and it should predict how this system evolves in fluid mechanics. And what we basically show is that by equipping this equivariance constraint, the network is much more data efficient and faithfully represents how a vector field should evolve and transform under certain group actions. So we compared to a standard ResNet, the resulting predictions are more crisp, as you see, trained on just 64 trajectories as opposed to 5,000. We can represent magnetic fields faithfully using this bivector space. And we can go to relativistic realms where we now have, we created a data set with moving charges, moving at relativistic speeds, and at various inertial frames of reference. And yeah, so here you see the result of that experiment showing that the network is much more data efficient, and the baseline ResNets, they seem to asymptote even with much more data. So yeah, to show here, we can boost our, so Lorentz boost our coordinates. And when we stabilize the frame, we see that the features learned are stable for our network, whereas for the ResNet, they are slightly moving in just one layer. So of course, if you stack multiple, then this will strengthen. And that's basically the last slide. So yeah, thanks.
So thank you, David, for this great talk. So do you have time for questions?
Thank you very much for that talk. It's really interesting. Can you comment, or did you calculate for the time series prediction with this multi-vector approach? Do you know how many Lyapunov times you can predict in advance below a certain threshold, like how stable that is in terms of whatever system you predict, how long you could predict that in an autoregressive way?
Yeah, I believe in this work we did not, but so the error accumulation is always like if you're worse in one step, then you will always be worse in several steps as well. There's no, at least in what I saw, there's no error correcting behavior in neural nets. But so usually, so that's why we just did one step prediction in this work. But what I saw in previous works also is that the errors grows exponentially, basically. So once you cross a certain threshold, it will just be.
Do you have any numbers for the threshold? Like there are equistane networks or other ways for time series prediction.
Yeah, but this completely depends on how what your delta t is. So, and also on the system, I guess. So I don't have these numbers ready from the top of my head.
Thank you very much.
Hi, thank you very much for your talk. I have a short question regarding the motivation behind the Clifford algebras, and I really need to look it up. And it seems to be that there's a universal property, so condition. This is the freest unital associative algebra fulfilling one equation.
Yeah.
Did you thought about, if you're aware of the condition I'm talking about, did you thought about to quantize this condition, so mainly deforming that algebra, so like the regularization story in the statistics they are doing with the lambda?
Ooh.
So the condition is like v to the square is equals to the quadratic form v times 1. So this is the basic the main equation, it seems to be, for the Clifford algebra.
Yes.
And imagine plus some quantized constant q, I don't know, then you get some deformation of your algebra.
No, I did not think about this, but this would, I think, yield a completely new object, which might have to be studied like quite fundamentally again. I'm not quite sure.
If the q getting smaller, then you came more close to your Clifford algebra. So
yeah,
maybe it's like a regularization term.
Yeah. Yeah, I also wonder what it does to your orthogonal group equivariance, because if you now square things and they do not give you the quadratic form again, I'm not sure if your network then remains equivariant to the orthogonal group, which is defined through your quadratic form.
Most likely that you soften up the condition so it's not equivalent anymore, but
right,
maybe you win something when you soften it up.
Yeah, so in that direction, there was a recent work where they do not fix the quadratic form, but they are able to learn it. And yeah, so I can forward you the paper if you're interested. And what's really interesting is that they get much better. They do the same experiments as we did with same architectures, and they get better numbers. And I think it's really interesting because they first train for the first 50,000 or whatever steps with this fixed quadratic form, equipping the network with all these inductive biases about different frames and so on. And then at some point they free it, and then basically the network for the last part of training can symmetry break slightly, getting even better results. And I think it's interesting because some of these tasks are not really like to the 20th decimal equivariant. So maybe the network can do some kind of correction there. Yeah.
Thanks for the talk. So you mentioned that whenever you have polynomials, essentially training becomes problematic for obvious reasons. And I think in, let's say, traditional equivariant neural networks, for example, when you use the Clebsch-Gordon tensor product as a nonlinear, let's say, activation, training seems to be problematic. And I was curious to understand how you guys solve this empirically with your proposed architecture. How are you guys actually dealing with the problem of the polynomials, which seem to be present in the CD tensor product?
Oh, so yeah, basically it's a combination of good initialization and layer normalization, equivariant layer normalization layers, which I did not discuss here today, but they are in the paper. And yeah, I did not see any problematic training behaviors when we did that so far.
Okay. You have presented a really general framework for. Can you comment about the limitations of your framework?
Yeah, so the one limitation is that although there has been a lot of work in framing certain physical theories using the Clifford algebra, you cannot represent arbitrary tensors, for example, because you're restricted to this multi-vector domain. So that's one limitation if you have tensor value data and you cannot somehow decompose it into something that can be expressed as a multi-vector, then you cannot use this framework.
What time for one question? If no, well, let's thank our speaker again.